Hello class 10th, welcome back. In today's video, we'll be discussing about concave and convex lenses. You might have seen people using spectacles for reading. The watchmakers use a small magnifying glass to see tiny parts. Have you ever touched the surface of a magnifying glass with your hand? Is it plain surface or curved? Is it thicker in the middle or at the edges? The glasses used in spectacles and that by a watchmaker are examples of lenses. Now what is a lens? A transparent material bound by two surfaces of which one or both surfaces are spherical forms a lens. This means that a lens is bound by at least one spherical surface. In such lenses, the other surface would be plane. A lens may have two spherical surfaces bulging outwards. Such a lens is called a double convex lens. It is simply called a convex lens. It is thicker at the middle as compared to the edges. Convex lens converges light rays. Hence, convex lenses are called converging lenses. Similarly, a double concave lens is bounded by two spherical surfaces curved inwards. It is thicker at the edges than at the middle. Such lenses diverge light rays. Such lenses are called diverging lenses. A double concave lens is simply called a concave lens. A lens, either a convex lens or a concave lens, has two spherical surfaces. Each of these surfaces forms a part of a sphere. The centers of these spheres are called centers of curvature of the lens. The center of curvature of a lens is usually represented by the letter C. Since there are two centers of curvature, we may represent them as C1 and C2. An imaginary line passing through the two centers of curvature of a lens is called its principal axis. The central point of a lens is its optical center. It is usually represented by the letter O. A ray of light through the optical center of a lens passes without suffering any deviation. The effective diameter of the circular outline of a spherical lens is called its aperture. We shall confine our discussion in this chapter to such lenses whose aperture is much less than its radius of curvature. Such lenses are called thin lenses with small apertures. If you hold a convex lens in your hand and direct it towards the sun, then focus the light from the sun on a sheet of paper and obtain a sharp image of the sun. On holding the paper and the lens in the same position for a while, the paper begins to burn, producing smoke. It may even catch fire after a while. Now, why does this happen? This is because the light from the sun constitutes parallel rays of light. These rays were converged by the lens at the sharp bright spot formed on the paper. In fact, the bright spot you got on the paper is a real image of the sun. The concentration of the sunlight at a point generated heat. This caused the paper to burn. Several rays of light parallel to the principal axis are falling on a convex lens. These rays, after refraction from the lens, are converging to a point on the principal axis. This point on the principal axis is called the principal focus of the lens. Similarly, several rays of light parallel to the principal axis are falling on a concave lens. These rays, after refraction from the lens, are appearing to diverge from a point on the principal axis. This point on the principal axis is called the principal focus of a concave lens. Letter F is usually used to represent principal focus. However, a lens has two principal foci. They are represented by F1 and F2. The distance of the principal focus from the optical center of a lens is called its focal length. The letter small f is used to represent the focal length. Now let us study the image formation by convex lens by watching an activity. First, take a convex lens and find its approximate focal length in a way described earlier. Place the lens on a lens stand. Place it on a central line such that the optical center of the lens lies just over the line. Mark 2f1, f1, f2 and 2f2 on the line. When the object is at infinity, the image formed is at f1, which is taken as the page which is on the stand. and the image formed is highly diminished, point size, real, and inverted. When the object is beyond 2f1, then the image formed is between f2 and 2f2, and the size of the image is diminished, and the nature of the image is real and inverted. When the object is at 2f1, the image formed is at 2f2, and the relative size of the image is of same size that of the object, and nature is real and inverted. When the object is between f1 and 2f1, the image formed is beyond 2f2, and the relative size of the image is enlarged, and the nature of the image is real and inverted. When the object is at focus or f1, the position of image is at infinity, and the object size is infinitely large or highly enlarged, and the nature of the image is real and inverted. When the object is placed between focus f1 and the optical center O, the position of the image is on the same side of the lens as that of the object, and the relative size of the image is enlarged, and the image is not formed on the screen, that is, it would be virtual and erect. If we perform a similar activity with a concave lens, and when we place the object at infinity, the image formed will be at f1, and the relative size of the image will be highly diminished and point size, and the image will not be formed on the screen, that is, the image will be able to see on the lens, that is virtual and erect. And if you place the object at between infinity and the optical center O of the lens, the position of the image will be between f1 and optical center O, and the relative size of the image will be highly diminished, and the nature of image will be virtual and erect. Now let us see how can we represent the formation of image by lenses by using ray diagrams. A ray of light from the object parallel to the principal axis after refraction from a convex lens passes through the principal focus on the other side of the lens. In case of concave lens, the ray appears to diverge from the principal focus located on the same side of the lens. A ray of light passing through a principal focus after refraction from a convex lens will emerge parallel to the principal axis. A ray of light appearing to meet at the principal focus of a concave lens after refraction will emerge parallel to the principal axis. A ray of light passing through the optical center of a lens will emerge without any deviation. Now let us take a look at the ray diagrams for the image formation in a convex lens for a few positions of the object. When the object is at infinity, then all rays will be parallel to the principal axis and will converge at f2 position on the principal axis. When the object is beyond 2f1, then the ray parallel to the principal axis will pass through f2, and the other ray will pass through optical center. Wherever these two rays will meet, an inverted image will be formed. The image formed will be real and diminished. When the object is at 2f1 position, we'll similarly take two rays, and wherever these two rays will meet, the image will be formed. And here we can see that the image formed is at 2f2 of same size, real and inverted. When the object is between 2f1 and f1 position, the image formed will be at beyond the 2f2 position, and it will be enlarged, real and inverted. When the object is at f1 position, the two rays will not seem to be meeting at all anywhere. So these rays will be parallel to each other, and so we'll say the image formed is inverted, real, and highly magnified and at infinity. When the object is between f1 and optical center of the lens, the two rays will also not meet here, and when we'll trace back these two rays, the image will be on the same side of that of the object, and it will be enlarged and upright, or we can say erect, and so the image formed will be virtual as it won't be formed on the screen. When the object is at infinity from a concave lens, the rays parallel to the principal axis will diverge through the concave lens and will appear to meet at the focus f1. So the image formed in this case will be highly diminished and at f1 position. And when the object is between infinity and optical center of the lens, the ray parallel to the principal axis will diverge, and when we'll trace back it to the f1 position, it will appear to meet to the ray which is passing through the optical center. Wherever they will meet in front of the optical center, there the image formed will be virtual, diminished and upright. For lenses, we follow sign conventions similar to the one used for spherical mirrors. We apply the rules for signs of distances, except that all measurements are taken from the optical center of the lens. According to the convention, the focal length of a convex lens is positive and that of a concave lens is negative. You must take care to apply appropriate signs for the values of u, v, f, object height h, and image height h dash. As we have a formula for spherical mirrors, we also have formula for spherical lenses. This formula gives the relationship between object distance u, image distance v, and the focal length f. The lens formula is expressed as 1 by v minus 1 by u equal to 1 by f. Similarly, the magnification produced by a lens is similar to that for spherical mirrors. It is defined as the ratio of the height of the image and the height of the object. It is represented by the letter small m. If h is the height of the object and h dash is the height of the image, then the magnification produced by the lens is given by m is equal to height of image h dash upon height of object h. And it is also equal to v by u. You have already learned that the ability of a lens to converge or diverge light rays depends on its focal length. A convex lens of short focal length bends the light rays through large angles by focusing them closer to the optical center. Similarly, concave lens of very short focal length causes higher divergence than the one with longer focal length. The degree of convergence or divergence of light rays achieved by a lens is expressed in terms of its power. So power of a lens is reciprocal of its focal length. The SI unit for power is diopter. So what is 1 diopter? 1 diopter is the power of a lens whose focal length is 1 meter. And remember that power of a convex lens is positive because the focal length of convex lens is positive and the power of a concave lens is negative as the focal length of a concave lens is negative. Many optical instruments consist of a number of lenses. They are combined to increase the magnification and sharpness of the image. The net power PA of the lenses placed in contact is given by the algebraic sum of the individual powers P1, P2, P3 and so on, as P is equal to P1 plus P2 plus P3 plus and so on. So this was all in this chapter. So for the numericals, we'll be doing that in our live classes. So thank you and have a nice day.